Let's start with a few examples of a very solved problem that goes under the name Schubert calculus on Grassmannians. Loosely speaking, this is about counting linear subspaces satisfying a collection of incidence conditions. Example 1, how many points in the plane lie on two lines? Let's make the lines blue and the points, or rather just the one point, red. Example number 2, how many red lines in the plane go through two blue points? Example number 3, how many red lines in space go through four blue lines? To describe lines in space, it's easiest to regard them projectively by adding one extra affine dimension. So what we're counting is elements of the Grassmannian of k-planes in n-space, and naturally it'll be much easier to consider complex n-space. Schubert first studied general problems of this type, counting k-planes in n-space satisfying a list of incidence conditions, and came up with rubrics for performing such calculations. The standard way to describe a k-plane, V, is to choose a basis of V, resulting in a k by n matrix, then to use Gaussian elimination to eliminate the choice. This results in a matrix with k pivot columns out of n total columns, and for each of these n choose k possibilities of where to jointly place the pivots, there is a complex vector space worth of possible k-planes V. It is called a Schubert cell. For example, in the fourth row, the space of matrices is one free variable, so is isomorphic to a one-dimensional complex vector space. The span of the two rows contains the fourth coordinate line, and lies in the coordinate subspace eschewing the first coordinate. Thinking projectively, we're considering lines in space that contain the fourth coordinate point and lie in the 2, 3, 4 coordinate plane, but until we consider closures, we're not considering the 3, 4 coordinate line. The closures of these cells, the Schubert varieties, can be described geometrically by incidence conditions, i.e. by putting lower bounds on how tightly V intersects the opposite base flag, written here at the bottom. There are several standard ways to index these n choose k Schubert varieties, a common one being indexed by partitions that fit inside a k by n minus k rectangle. However, we'll prefer to index Schubert varieties by binary strings, with zeros at the pivots and ones at the non-pivots. Hilbert's 15th problem was to put Schubert's calculus on a rigorous footing. It inspired the development of cohomology rings. Because the decomposition above of the Grassmannian is into Schubert cells of even real dimension, their closures, the Schubert varieties, give us bases in homology and cohomology, and the intersection theory questions from before become computations of the multiplication in this basis. Another class of rings with bases is representation rings of groups, and Lisieux noticed in 1947 that the Grassmannian's cohomology ring is related to the representation ring of GLK in a basis-respecting way. This shows, in particular, that the structure constants in the cohomology ring are non-negative, and the whole game for us is to compute these structure constants in a manifestly positive way. It is worth noting that cohomology rings should not be expected in general to have bases with positive structure constants. The cycles one wants to intersect, one cannot usually make both complex and transverse at the same time. The special feature of the Grassmannian, as recognized by Kleiman in 1974, is that it is a homogeneous space. In all the rings with bases to come, we have alternating sum formulae to compute the structure constants, and frequently we have abstract proofs of positivity. The unsolved questions concern finding positive combinatorial formulae. Question? Yes. Why is it so important or interesting to find combinatorial formulae for these cohomological numbers, counting Young tableau or puzzles or whatnot, if we can already compute them? That is an excellent question, with several answers. One is that it is much easier, theoretically, to prove that a number is non-zero if one need merely exhibit one instance of some combinatorial object, secure in the knowledge that its contribution won't be taken away by some other term. Similarly, it can be much easier to prove in this way that a number is zero. Computationally or experimentally, positive formulae have been much faster than alternating sum formulae. I'll give an example later, but I hope it's intuitive that a formula that works against itself might be less effective than one that doesn't. I suppose a positive formula might also point toward potential categorification, souping up the integers to dimensions of vector spaces. That's another good reason. Have a cookie. Thanks. Where were we? Yes. I started by saying that Schubert calculus in the cohomology of Grassmannians is a very solved problem. And we will talk about a solution soon, but first I wanted to discuss some natural generalizations of this basic problem, only some of which have known positive solutions at this point. The structure sheaves of the Schubert varieties define a basis in the K-theory. Of course, the ring involved is no different from cohomology rationally, but the two are different as rings with bases. The coefficients are not actually positive, but rather come with predictable signs. In Book's formula, they count set-valued semistandard tableau. The Schubert varieties are invariant under the action of the diagonal matrices, since that group, called T for torus, preserves the standard flag. As such, they define a basis of T equivariant cohomology, but now the coefficient ring is not Z, but is rather the T equivariant cohomology of a point. That is a polynomial ring, and the positivity property concerns coefficients of these polynomials. This equivariant positivity was first proven geometrically, i.e. ineffectively, by Bill Graham, but is manifest in our puzzle formula. Flags. This is the one that keeps me up at night. Chains of D nested subspaces instead of single subspaces, the D equals 1 case. Of course, D equals N is the richest case. I conjectured a positive rule in 1999, a beautiful rule, an awesome rule, an incorrect rule in general. For D equals 2, though, it was proven 15 years later. It was conjecturally corrected for D equals 3, and then that proven for D equals 3. For D equals 4, there is a corresponding rule, but it is not quite positive. The small quantum cohomology of general flag manifolds remains quite mysterious, but rather oddly, computing its structure constants in the Grassmannian case can be reduced to ordinary Schubert calculus on a two-step flag manifold. The numbers one wants are intersection numbers on a Conserved moduli space of stable maps, and this moduli space is geometrically close enough to a two-step flag manifold that one can transfer the integrals to the latter. There's too much work on orthogonal and symplectic Grassmannians to summarize here, but I will mention the work of Thomas and Yang on other groups' homogeneous varieties that behave most like Grassmannians, the cominuscule flag manifolds. The newest direction of the field is toward cotangent Schubert calculus, in which the relevant varieties are certain Schubert-like Lagrangian cycles inside the cotangent bundle. These are connected to many things, characteristic cycles of D modules or of perverse sheaves, and from there to representation theory. Moreover, the cotangent bundles are examples of Nakajima-Quiver varieties, which we will get into later. Any of these generalizations can be mixed and matched, and most of the combinations are known for geometric reasons to be positive, but very few of them have positive formulae as yet. In addition, there are other problems of a similar flavor, such as affine Schubert calculus and pullbacks of Schubert classes from one flag manifold to another, that I won't touch on at all. Terry Tao and I, knowing nothing about the questions or answers in Schubert calculus, invented these three puzzle pieces in service of a completely different question. Meanwhile, Klyachko had been answering the same question using Schubert calculus on Grassmannians. So quite by accident, Terry and I had invented another Littlewood-Richardson rule, i.e., a rule to compute products of Grassmannian Schubert classes. The threefold symmetry of puzzles, a symmetry which is not evident in the original Littlewood-Richardson rule, relates to an alternative way of computing the constants using a self-duality property of the Schubert basis. There's another symmetry coming from Grassmannian duality, which can be seen on the puzzle level by flipping them over. The only missing symmetry is commutativity. This self-duality of the Schubert basis does not hold equivariantly. So to compute those structure constants, we introduced a piece that cannot rotate and contributes a factor of yi minus yj based on its location in the puzzle. A few people noticed quickly that Book's rule for K-theory of Grassmannians can be implemented with one new puzzle piece, but it wasn't until 2016 that Wheeler and Zingestan noticed that the rotated piece lets one compute in the dual basis of K-theory. There are more pieces to add for 2- and 3-step Schubert calculus, but we'll focus on the Grassmannian case, the one-step case, hereafter. The puzzle formula in equivariant cohomology is a sum over products. This suggests, or rather it should have suggested to me and Terry 25 years ago, that this formula is computing a matrix entry in a big product of matrices. It's easy to write down these matrices. It was Paul Zingestan who in 2009 reformulated the equivariant puzzle rule in this way, and he noticed an amazing property of the matrix R, the Yang-Baxter equation. This equation is an analog of the third Reidemeister move from knot theory, and people have studied its solutions for decades. These solutions are conventionally called R matrices, which is a pity, as based on their tetravalent shape, they should quite obviously be called X matrices, to fit nicely with Y matrices for trivalent vertices, and K matrices for when a path bounces off a mirror. I am pleased to report that K matrices are indeed standard terminology, and will grudgingly use the R matrix terminology hereafter. Drinfeld and Jimbo showed that one could cook up solutions to the Yang-Baxter equation as intertwiners of tensor products and representations of quantized affine algebras. More specifically, the R matrices appear as commutors for these non-co-commutative algebras. Nakajima realized some of these representations geometrically in the K-theory of Quiver schemes. Malik and Akunkov connected these two, obtaining the R matrices directly in terms of correspondences between the Quiver varieties. Note that D-step flag manifolds are not quite Nakajima Quiver varieties, rather it is their cotangent bundles that are. This leads both to complications and to new opportunities. Recall the triangular puzzle pieces for computing the product in the cohomology of the Grassmannian of K-planes in Cn, corresponding to the non-zero entries in this matrix U. Under the assumption that our R matrix arises in the Drinfeld-Jimbo way, we should be looking for a quantized loop algebra with three-dimensional representations. We could even use the puzzle pieces to constrain the possible weights of these representations, but such subtleties are unnecessary in this tiny example. The obvious guess is to consider the fundamental representations of SL3. This C3 and alt square C3 are the representations corresponding to the first and second fundamental weights of SL3. We'll need the nth power, and following the Quiver variety indexation, we denote these representations by attaching nodes to the Dinkin diagram A2. This is more than we want in that it's about puzzles with arbitrary boundaries with any combination of zeros, ones, and tens. We only want zeros and ones on the boundary and a specific number of each. On the representation side, specifying the content corresponds to focusing attention on specific weight spaces. The corresponding Quiver varieties are very simple, each secretly isomorphic to the cotangent bundle of a Grassmannian, which suggests that we're on the right track. We haven't discussed the indexation of the weights yet. The weight associated to a quiver is the sum of the fundamental weights in the framed vertices minus the sum of the simple roots in the unframed vertices. If we actually compute the intertwiner of these representations of quantized loop A2, we get a different matrix. The representation theory wants us to include a puzzle piece with tens on all sides. Why is that? The representation theory is solving a harder problem, multiplication in a subtler basis than the Schubert classes. In 2017, Paul and I knew that the R and U matrices derived from puzzles were degenerate versions of the R and U matrices supplied by the A2 Yangian representation theory. It then took us a few more years to connect the dots with the cotangent bundle, thereby giving a geometric interpretation of this richer multiplication. Here's a down-to-earth application of this richer multiplication. Take three Schubert cells in the Grassmannian and rotate them using generic group elements. Let M be the transverse intersection. Then -1 to the dimension of M times its Euler characteristic is counting a certain number of puzzles, including both 10-10-10 pieces, both the delta and the nabla. In fact, each of these puzzles has exactly the same number of pieces, which is that dimension of that intersection. In the case that M has dimension 0, this formula for the Euler characteristic reduces to the usual Schubert product formula. As of summer 2022, we are in the historically rare situation of having a positivity result that we know only combinatorially, with no geometric proof of positivity. Our combinatorial proof holds for 1-, 2-, and 3-step flag manifolds. Let's go back to the Quiver varieties suggested by the puzzle R matrix. There isn't a natural function between these cotangent bundles, but there is a natural correspondence. We start with the diagonal inclusion of the Grassmannian into its square, take the graph of that function, which lives in the Grassmannian times the Grassmannian squared, and then, in either order, take the transpose of that graph and take its conormal bundle. The diagonal inclusion map induces a linear map backwards on cohomology, which is, of course, the product structure we're investigating. But we don't need an actual map of spaces. The correspondence is already enough, or pretty much. To be more honest, issues arise related to the non-compactness, and this will be the reason we work with localized equivariant cohomology. The representation theory suggests a natural intermediate representation, or more precisely, an intermediate weight space. We know, of course, a geometric interpretation of that weight space is a Quiver variety, and a simple one at that. What would be nice at this point would be to geometrically interpret the module maps in line 3 using correspondences. At this point, we can describe Malkin and Kunkov's geometric interpretation of R matrices. Remember that the Schubert varieties were defined relative to the base flag, and defined elements in T-equivariant cohomology because the base flag is T-invariant. The same is true for the Segre-Schwarz-McPherson bases we need here. But if we change from the base flag in Cn to another T-invariant flag, of which there are n factorial choices available, we get a different basis. When two coordinate flags are adjacent in a certain sense, the change of basis matrix between their Segre-Schwarz-McPherson bases is the R matrix. In the case at hand, the natural basis for the intermediate space, the cotangent bundle of this two-step flag manifold, doesn't behave simply under the L2 transformation. There's a different basis, not for an adjacent basis, but one that's n choose 2 steps away. And the n choose 2 R matrices let us change from the basis we want to the basis that L2 likes. Then L2 induces the map U tensor to the n, killing most basis vectors and taking each remaining basis vector to another basis vector, up to an overall constant factor gamma we compute. So, this is the geometric interpretation of puzzles. Most of the puzzle is about a change of basis on an intermediate space, which in this case is a certain two-step flag manifold, or rather its cotangent bundle. The last part of the puzzle is induced by the Hamiltonian reduction. The constant factor gamma, which we didn't get into here, is a product of n choose 2 simpler factors gamma ij, which for bookkeeping purposes we distribute among the R matrix steps. In particular, the contribution of a rhomboidal puzzle piece isn't quite the corresponding entry in the usual R matrix. Rather, it's that entry times gamma ij. I haven't explained how we use the content on the boundary of a puzzle, namely k0s and n-k1s on each side, to pick out a particular weight space in C3 tensor to the n. Consider a proposed set of puzzle pieces, and make a free abelian group with a basis vector for each label on each edge. So in this case, there are 9 total. Then impose a linear condition for each puzzle piece. In the case that one's puzzle pieces come from the U matrix of some fusion of representations, the resulting abelian group will be the weight lattice, and for each of the 3 sides, the associated basis elements will map down to the weights of those representations. Moreover, if the representations are minuscule, then there will be a form on the lattice with respect to which all the weights have the same norm. In early 2017, Paul idly asked me the physicist's question, what are the locally conserved quantities in a puzzle? And thinking about that, we hit upon the above recipe as a way to reverse engineer the representations from the puzzles. We carried out this quotient space calculation for the known puzzle pieces at d equals 1 and 2. Remember, d is the number of steps in our partial flags. The then conjectural pieces at d equals 3, and the pieces that my failed conjecture suggested at d equals 4. Let's return to the Grassmannian case d equals 1, where the northwest and northeast sides lead to the same representation with the same weights, C3. There is a subtlety, though, which is that a 0 on the northwest side does not have the same weight as a 0 on the northeast side, rather a 1 on the northeast side. So while this numbering system was good for seeing the threefold symmetry, it's not good for seeing the local conservation law of the puzzle pieces. After suitable changes to the puzzle boundary conditions, this new system of puzzle pieces below is logically equivalent to the old one above. But now, the edge matching condition, i.e. the jigsaw puzzle condition, amounts to demanding that pipes only have ends on the boundary of a puzzle. About a decade before a book Kresh, Prabhu, and Tomvakis proved my two-step puzzle conjecture in 2014, Andre's book computer tested my rule up to n equals 15. I was quite impressed by this, because the alternating sum methods of calculation, e.g. using Schubert polynomials, peter out around n equals 8 or 9. And mind you, this problem grows much faster than linearly. So how did Book do it? He computer checks that the puzzle multiplication works correctly on generators, and he computer checked associativity. That is, he checked the puzzle rule against itself, and that was enough to rigorously establish it for a given size. 15 versus 9 growing something like n factorial cubed, that's how much more efficient this positive rule was than other non-positive means of calculation. Around 2003, André Henriques pointed out to me that this associativity equation, counting two sets of bipuzzles, can be interpreted as happening on the front and back of a tetrahedron. In particular, there might be a bijective proof of this associativity using 3D puzzle pieces. In fact, he found some such pieces, but they were then lost and too painful to reconstruct. Can we use the Quiver story to discover new ones? The Quiver story we set up to understand multiplying two classes easily extends to 3, but now we face an A3 quiver and a map from C4 tensor cubed to alt cube of C4. In particular, it becomes very unnatural to try to work with the Z3 symmetric pieces from before, like poor André was doing, but it's easy to extend the puzzle rule with the new set of pieces, just add a fourth color. What you see here is a size n tetrahedron full of mysterious 3D puzzle pieces. The top bears two puzzles, one in blue, yellow, green, and the other in red, yellow, green. Each 2D puzzle is of course broken up into triangles and upside down triangles, which one should think of as having 3 choose 1 and 3 choose 2 vertices respectively. One dimension up from that, the 3D puzzle is naturally broken up into a unit tetrahedra with 4 choose 1 vertices, into upside down tetrahedra with 4 choose 3 vertices, and into octahedra with 4 choose 2 vertices. It is worth noting that there can be no symmetric choice of these 3D puzzle pieces. The linear algebra wants octahedron removal to take a puzzle labeling of one bumpy surface to a linear combination of other bumpy surfaces, rather than to a single such. What was lucky was that a consistent choice could be made. There won't be any such lucky choice in the equivariant version, but this is no surprise. We have no reason to expect there to be the same number of bipuzzles, one way versus the other. Remember that we had an example before where equivariant commutativity could not be established by correspondence. Let's look one more time at the correspondences we used to study Grassmannian Schubert calculus. Perhaps the easiest way to generalize this is to change one k to an independent variable j. The geometry doesn't change much. The composite of the two correspondences is the transpose of the conormal bundle, of the graph, of the natural inclusion that is no longer the diagonal inclusion. For 20 years, behind my back, these self-same d equals 1 puzzle pieces were doing a significant part of d equals 2 Schubert calculus. One of the tools we need in order to study larger quiver varieties is Nakajima's reflection isomorphism, where an unframed label is replaced by the sum of its neighbors minus the original label. There are some subtleties having to do with stability conditions that I will skip over. With these, we have a lot more ways to obtain quiver varieties that are isomorphic to T star of partial flag manifolds. For example, consider the following correspondences generalizing the factorization up above. The first two quiver varieties are obviously cotangent bundles of partial flag manifolds, where the left one only has subspaces of dimension up to 3, and the right one only has subspaces of dimension 3 and above. But what is this bottom variety? We can use Nakajima reflection isomorphisms to shrink this vector, replacing the 11 by 12 plus 3 minus 11, which is 4. After a sequence of such reflections, we get a quiver variety we recognize. This factorization, where the 3 and 8 are suitably generalized, led us to create one of the most general applicable formulae in full flag manifold Schubert calculus. It computes products of Schubert classes, or Segre-Schwarz-McPherson classes, one of which only involves subspaces of dimension up to k, the other only subspaces of dimension from k up to n. On the geometric representation theory side, we expect that any map of standard modules for quantized loop algebras should be associated to a Lagrangian correspondence of quiver varieties. It was known how to geometrize the obvious maps of tensor products, namely to Malkin and Kunkov stable envelopes. and Paul and I found ways to geometrize a few intertwiners coming out of reducible tensor products. At the moment, the representation theory is better understood here than the geometry, but there's plenty to learn on both sides. After the puzzles led us to certain A2, D4, E6, and E8 intertwiners, we realized that geometry suggests new intertwiners, which led us to some of the most powerful Schubert calculus formulae to date. How much more flag manifold Schubert calculus can we dig out of this framework? More generally, we can use the same correspondences to study maps in cohomology on general quiver varieties. Can we use this technology to compute cohomology rings of quiver varieties that aren't flag manifolds? For that matter, can we fit non-type A flag manifolds into this framework? We have one result in this direction, computing a pullback along an inclusion that isn't a diagonal inclusion. Thank you for coming to my talk, and special thanks to my co-authors, to the ICM committee, and to my video editor, Taryn Knutson.
Sweet.